combination for parallel resistors. So before we dig in, I wanted to actually show you that this stuff really works in the real world. I'll just wait a moment before I switch over to these cameras. There we go. All right, so just sing out, as my mother used to say, if you want me to bring this slide back. And then we see a power supply. The meter is set up to show current. And this is just an overview of what I'm doing. And so what I've got here, I have set up this guy right here. Although I have actually, I put smaller resistors. So this is, well, it's very similar to this. I don't want to, well, we might as well, let me bring up exactly what I have here. Because this is using the different circuit board. Here we go. All right. Of course, it's laggy. So, ammeter, yep. So I have the ammeter here. That's the one that you see in this window here. So it comes out of the power supply and it goes into the ammeter first. And in this case, so I have it a little different. Let me show you the way I have it set up. Come on, I want to delete that. So I have the power supply going straight to the ammeter. And then from the ammeter to the positive rail, like that. That's what I have. And then I have 3 resistors. And I have some jumpers. And I have a digital voltmeter. That's this one here, this little guy here. You notice it's showing approximately the same voltage as the power supply is showing me. And so now you can see the 3 resistors here. I can't zoom this, but I have 1, 2, 3 resistors. And this is coming from the ammeter, and it goes up to the positive rail. And then I have these jumpers ready to go, 3 of them, to go to the resistors. This is going to the voltmeter. You can see the wire wiggling there. Then on the negative rail, I have this black one going back to the power supply. And then I have the one for, this is the black for the voltmeter. And the next jumper here. And then these are the three, they go from the resistors down to the negative rail. So you notice now I'm measuring the voltage from the rails, and it's showing 10.63. I don't quite understand why the power supply changes it when it must be something wrong with it, because it's not supposed to change its voltage when I ask for more current. It's supposed to keep the voltage steady up to a limit. So I'm a little wondering why it's doing that. But first of all, let's do a little exercise here now. So let's write down I of R1, I of R2, I of R3 in our books. So you make a note to yourself, Dr. H showed us a real circuit, and well, look, I can, let's see, what's a good thing to do here? Yeah. Oh, wait a minute. I could just do a screenshot of this and then send you the screenshot at some point. Yep. That's it.
Professor?
Yeah, question.
So what are we trying to demonstrate here?
Oh, I'm getting there. Yeah. So write down on your books I of R1, which is why don't I do it on the screen? I'm doing it in my own logbook. So we're writing down I of R1 equals I of R2 equals I of R3 equals, and I total equals. So we're just, at the moment, we're going to examine a parallel circuit. And so you can write in your logbook that Dr. H showed us a real parallel circuit. And it looks very much like our TinkerCAD sim. So the voltmeter, the DVM, is measuring delta V of the rails. And that's simply this red part up here, these holes, that's the positive rail and the negative rail, because the resistors are attached or at the moment, I have, from this picture, I have all the green on the bottom, but I don't have these yet in place. I have them ready, but they're not plugged in yet. Okay. So let's do another screenshot here so you can have it if you like. So we're just doing a quick study of a parallel circuit just to show you that indeed the real one does what the TinkerCAD does. That's all. Okay, so the ammeter is measuring I total, but let's just hold off on writing anything down for I total, because what I want it to be is I total of all three resistors. So I'm going to now connect the first resistor into the circuit. And we notice, I see 0.087 amps. And that is because, and that's IR1 because it's the only resistor connected. So now I'm going to disconnect, and you see the voltage. The voltage changed a little bit. That's the voltage across it. So we're going to get a little bit of error out of this, but I think we'll see. Let's check. So this, now I'm plugging in only R2. Oops, this thing is beeping. It wants to go into power saver mode.
Professor,
Yo.
when you're saying I'm plugging in, you mean the power supply is going into nothing but that resistor?
That's
And
correct. That's right. Good for you. That's exactly right.
it's being read.
Yep. Let me show you in TinkerCAD. Where is it? So first I did is this is the first thing I did. I put a wire from the rail to R1. So let's restore that. So I've already got the 3 wires on the bottom. And now I'm plugging in a jumper from the rail to R1. And let's start the simulation. And okay, let's make this the same. Let's see, we should get similar numbers. Let's see if we do. And so this is saying 66 mil. Oh, because my resistor is slightly different. That's why. So we see 87 milliamps, and they're seeing 67 milliamps. And I don't remember the volt. This one. Oh, okay. Well, anyways, I don't want to give away everything. And notice that, oh, I don't have a voltmeter attached. Okay, I need a voltmeter. I have to stop the simulation. So let's put the voltmeter the same way I have in the in the real one. I have it going to that rail. And I have it going to this rail. Okay, and I'll screenshot it. So now you see this resistor has 10 volts across it. And in this case, it has 66.7 or 67 milliamps. In our case, because we have a somewhat different resistor and I can't set this voltage to be exactly 10. The knob is too finicky. But, oops, this thing went into power saver mode. Excuse me a moment. So this thing is showing us 87 milliamps, 0.087 amps. That's IR1, don't forget. So it's 0.087 amps. So now I'm going to unplug R1 again, and disconnect it from the rail, if you will, because I'm not actually unplugging the resistor. I'm unplugging this jumper. And now I'm looking at R2. And I see the voltage change slightly, but luckily it's not too badly. So this is now 0.047 amps. And now I unplug R2, and I put in R3. And the voltage is staying fairly constant. That's nice. And that shows us 0.031 amps. Now, what? So you can, one thing you can notice now, if I go back, I plug in R1, I see something. I plug in R2, we should see the current increase because now I have more current paths. And then I plug in R3 and it increases even more. Not a whole lot. That's good. And so here, 0.167. So let's see. We have 0.087, 0.047. I'm just got my fingers crossed. I don't even know if this is going to work or not. 0. I have faith in the laws of physics. So, and of course, I didn't leave any room. 7 and 7 is 14, and 1 is 15. Carry the 1. So that's 8, and 8 is 16. Not bad, huh? Remember, plus or minus 10%, we're happy. And the discrepancy is coming because there's something wrong with the power supply. And remember, the voltage would change a little bit each time. So at least we verify that the current is the sum. The total current is the sum. And in fact, we know that, remember I said that, where's some room for this? I total equals V total over R total at all times. So we can already, and you're going to do this in the tables. R total is V total over I total. And that's, what is it? We got 10.55 divided by 0.167. And we can get a number there. And then we can also use, you guys will know the values of your resistors. I know the values of mine. I didn't write them down, so I have to look at the color codes. But I can then say, all right, when I do the math and add them together by math, does it equal what I get from this measurement here? So this is our total measured, and we want to compare our total measured to our total calculated. And I'll go over that with you as we do it.
Professor?
Question.
Another quick question.
Of course.
So you said the yellow meter is showing us amps, right?
Correct.
And what's the significance of the amps again? I'm not.
Oh, it's the amount of flow, the amount of current flowing.
Flowing where? Through the whole system?
Well, yeah, it depends. At the moment, it's flowing. Okay, good. Let's take a look. So the way, you can't see it all, but this is connected. It comes out of the power supply, goes into this ammeter. It comes out of this ammeter and gets connected, and it's this wire right here, this clamp, this clip. So now it's flowing here to here, and it's going into the rail. Now, because I have 1, 2, 3 jumpers to R1, wait a minute, hold on, save this. No, I wanted to make this bigger, but I'm afraid. Oh, let's stick with it. We have our 3 resistors, R1, R2. I don't know if you can see this. And I have the 2 white ones, and the blue jumpers go from the rail each to one of the resistors. And then at the other end of the resistors, I have the 2 yellow jumpers and the 1 blue jumper are taking it from the other end of the resistor to the negative rail. And then it's traveling, first of all, here to this black wire. And this black wire is coming here to, that's this black wire over here on the left, back to the power supply. And at the same time, this red wire here is this red wire, and it's going into the voltmeter. And it's connected also to the positive rail. And I think it's off the screen. Yeah, this blue jumper here, I'll bring it onto the screen. That blue jumper there, you see, it kind of obscures things, is this goes then to this black wire, and that's the black wire here into the voltmeter. So the one on the left is an ammeter, the one on the right is a voltmeter. See, it says DC volts here, and here it's pointed to A for amps on the left.
And the amps increased as we put more resistors into the equation.
Right, exactly. Because it's a parallel circuit. A way to think of a parallel circuit is multiple current paths. And so if I keep adding current paths, I get more current. Total current. This is why if you ever, your parents yell at you to turn lights off, if you were to go out and look at your electric meter, you would see, well, I don't know if they have a spinning dial anymore, but like mine is digital, and you can see it counting up the number of kilowatt hours. Excuse me. If we turn on, we have a gas stove and a gas dryer, but even so, if I turn on the dryer and maybe the dishwasher, you'll start seeing it go much faster because you're using more current. Oh yeah, FYI, everything in your house is parallel. I think I've saved this screen, but I'll make absolutely certain and save it. So I'm going to clear this. It's okay if I clear all the writing on the screen? Just, oh yeah, I can hit undo. So if somebody goes, no, wait, I can hit undo. Where is it? We got to watch the time. Mouse. What did I want? I wanted the slides. I think they're hidden here. Hold on. Yeah, here we go. So I don't know if you guys, they're not really prevalent anymore, but you might remember these Christmas tree lights. When one of them burns out, they all burn out. But in your house, you have the 120 volt wire come in, and you have the 0 volt wire come in. So then you might have a light bulb, and of course there's a switch, another light bulb, and then you might have your dryer. But the point is that if one of the light bulbs burns out, the rest of the light bulbs stay on. And also so your house is parallel. And what happens then is that everybody gets the same delta V. So then when the people who manufacture these objects, they know that what the voltage is, and then everybody gets the current they get I that they want or they need. Because it's ultimately the current that does the work, not even though we talk about voltage as a potential energy per charge, we always think in terms of the current, because it's the current through the coils of a wire that create the magnetic fields, and then it's the current flow through the filament of the light bulb, making it glow because it's hitting the molecules in the filament.
So
sorry, Alex. Go ahead, Alex.
I'm good to ask, Professor.
Sorry?
I'm good to ask. Sorry, I cut you off.
Oh, no, I cut you off, so ask away.
Thank you. So in this case, each one of these things, can we consider them to be resistors in and of themselves? Because
yes, absolutely. That's why I said, I don't know if you were here at the very beginning, but you think of electricity as energy, and you think of your battery or your power supply or your generator at the Hoover Dam is adding energy to the charge carriers. And then you're sending the charge carriers somewhere to do something useful, to do some work for you. And for us, it means to make light or to run a motor or even to heat our house. And they can all be considered resistors. That's right. Very good, Alex. You're paying attention. Just, I don't mind if people don't remember every blessed thing I say, but you definitely are picking up on the concepts when you ask that question.
Lastly, Professor, the significance of the amps here, what does that tell us again?
The amount of charge carriers? Good. What's an amp? An amp is defined as the number of coulombs per second. So the number of charge carriers passing per second. So the voltage they all have the same energy from the battery. So to deliver more power, we need to give more current. That's why I'm saying that it's all, you basically, series circuits are all well and good. We rarely deal with them in the everyday world. We mostly deal with parallel. So everybody gets the same voltage, the same energy per charge carrier. And to get more work, we just got to give it more charge carriers, more current. And by the way, guys, in general, this is not super important that you understand this in a deep way for Physics 1200. Alex is asking, and I'm supplying the answers. And I hope I'm making it simple enough. Yeah, I think I am. So batteries, power supplies, give each charge carrier a certain amount of energy, and the amount of current tells us how much of that energy is being delivered. Okay, what are we doing? We have 1 hour left, but that's all right. I think I've provided enough information in the slide 5. Sure. Wow, Ita, I wanted to say something earlier. Did it go? Yeah, there it is. So the important thing, this was the discussion about how you can survive this because you don't have any delta V. The most important thing here is that you have the complete circuit, and that means that you get a delta V over the thing. So this is your item that you want to do work, right? So Alex, right? This is the R represents the things that we want to do, the work, the things that we want to get work out of. And unless we supply a difference in voltage across it, no current flows, no work. So if we don't complete the circuit, there's no delta V, meaning that the resistor will be 5 volts on either end of it. So no delta V.
So whenever we add more resistors in parallel,
Yeah,
the amps increase.
that's right. The total amps will increase. That's correct.
And
The
that means there's more draw
there's
on.
more pathways. Okay, let's summarize this. I'll make a new slide. Okay. So this does help you understand what's going on with the resistances. So if I have here, let's see, now I have my R1, and now let's say I have my R2, and I have, this is a switch, these are switches, R3. So we have I1, let's go S2, S3, and so I2, I3. So with S2 and S1 open, I total equals I1. And that's S3. So S2 closed, S3 open, then I total equals I1 plus I2. Now, if I have S2 and S3 closed, then I total equals I1 plus I2 plus I3. Now, in a series circuit, and if I have R1, R2, R3, and now I have now we have S2. Now notice now S2 and S3 are closed. So that means that the current is going to go, it's not going to go through the resistors. So we have V battery. So now with S1 and S2 closed, I total equals V battery over R1. And I keep doing this, S3. Now, with S2 open, S3 closed, then I total equals V battery over R1 plus R2. So now the current goes down. Excuse me. And if I then say S2 and S3 open, then I total equals V battery over R1 plus R2 plus R3. Now notice in each case, that's our total. For a series, this is the series, of course. So in a series circuit, every time you add something, the current goes down. The problem then is, though, that everybody gets a different delta V. Everybody gets a different, they get the same current, but they don't get the current they want. So you're not getting, you don't get the work out of it that you expect. And that's why we don't usually use it. Or we usually use, we almost always use parallel in the everyday world. Make sense then, Alex?
Professor, something
Yeah.
comes to mind in terms of I hear people talking about batteries or power supplies and stuff, and they say you could have like 1,000,000 volts, but if you don't have amps, the right amps, it's not going to do much for you.
Oh boy, that's exactly right, Alex. And you
What is
know
that?
what? We have to have this conversation another time. Good for you. That's very astute. That's why we use power supplies in the class, because if I used a battery, batteries can only supply a limited amount of current depending on how big they are. You may, you have triple A, double A, and C and D batteries. Excuse me. And you notice they all say 1.5 volts. The thing is that the D battery can supply more current. That's right. If you don't have enough current, then the voltage will droop. And that's why, if you noticed earlier, I was commenting that the power supply the voltage was drooping when I was asking for more current. And it's not supposed to do that. It's supposed to stay steady. Very good, Alex. I'll give you a little, I can point you at, or I'll create a little discussion, or if you want to come visit me in office hour, and I can answer these questions for you. Okay. But not that I don't enjoy these questions, but we have to finish. Well, like, we're not going to finish, but we want to get something done here. At least I need to show everybody how to do things before we say
Absolutely.
goodbye. Okay, great.
Also, Professor, so we're not talking about batteries. So in that case, the machine that we do have, it is delivering any amount of amps that we require.
Basically, I can give a quick summary of this. And
Because I was having trouble understanding how come our amps are going up even though we're
yeah,
wait.
right, because the power, exactly, as you say. So uh what happens is, if I make a plot like this of current and voltage, and now we're talking about batteries, not resistors, right? So if I did this with because let's give me a minute. V equals IR. Then if I made this plot for a resistor, it would just be a straight line, and with the slope equal to R, because I would just multiply R times I, and I'm going to get V. So that's a resistor. A battery, though, is a little different. So what happens is you have what's called the EMF, or the nominal voltage. So nominal voltage, and this is what's written on the label. But if you start asking current out of the battery, it basically starts to do this. And it depends on the size of the battery, what the slope of this line is. And depending on what current you ask for, so call this I1, if I measure the voltage here, V1, which is then an example of it's called terminal voltage. Oops. See, I told him I was going to do this offline, but it's a question that's relevant to all of us, so you understand why we use power supplies. So basically, I mean, in fact, they basically just go straight down. They don't even have this little plateau. A power supply, on the other hand, though, is made with active electronics, so that it goes like this, and then all of a sudden you reach its limit, and it just dies out. So you may notice, even in TinkerCAD, the TinkerCAD can only supply 5 amps. If I take TinkerCAD and let's say if I put a wire from here to here. So I made a short circuit. Notice it went to 0 because it can only supply 5 amps. So there's no volt, just like I drew here, it just crashes right. It doesn't go quite straight down. If we put it, if I added like some small resistance, we might see like 3 volts. Or, in fact, we're going to see that kind of effect today if we get to the lab. I'm digressing too much, but I enjoy great questions. Okay.